Hi and welcome back. In the last video we showed how to graph exponential functions. Now let's just do some problems with exponential functions. So these are what I call growth and decay problems, right? So let's just move here. So we're going to do some growth and decay problems. This is decay. Okay. So there is basically a general equation for growth and decay problems. So I'm just going to write that down. So this is A final, which stands for the final amount. A naught, or A initial times R to the power of T divided by H. So A final just means the final amount. A initial just means, obviously, the initial amount. R is either the growth or decay rate. And H is the time to reach the decay rate. Okay, so just make sure you have this formula here, and I'll explain how to basically get all these quantities in a second. So let's say, for example, we have a problem, okay, and it has the following statements, okay, and based on these statements we will define. So here's the statement, and based on the statement we'll determine what R is, and we'll determine what H is. Okay. So say, for example, something doubles every minute, okay? If something doubles every minute, R has to be 2 because it's clearly doubling. And since it's every minute, in other words, per minute, so since H is the time taken to reach the growth rate, H would be 1, right? Because it's per minute, so it doubles every minute. So that's what that would be. What happens if it, say, triples every minute? So in other words, that would be 3, and once again, since it's every minute, H would be 1. Okay, what happens if something grows by 4% per year? So if something grows by 4% per year, that means initially starts from 100%, which we define as 1, plus 0.04. So in other words, that is 1.04. So the R in this case is 1.04. And since it grows per year, H would be 1. Okay, I hope that makes sense. So it grows by 4% per year. What we're doing is 4% as a decimal is 0.04, and we're adding that to 1. So since it's growing, it has to be greater than 1. Remember, the B value has to be greater than 1. So it's 1.04, and H is 1 because we stated that it's per year. Okay, so let's continue. Actually, instead of that, maybe I can just scroll down and just extend the page a little bit. Okay, so let's just extend this. There are a few more statements that I have to go through. So what happens if we say something decays, right? So decays by 3% per year. So if something decays by 3%, what that means is it's 1 minus 0.03. So the R value would actually end up being 0.97. Okay? And once again, since it says per year, H is just 1. Okay, does that make sense? Decays, so it has to be less than 1. So 1 minus 0.03, which is 3% as a decimal, is 0.03. And there we go. Okay, so what happens if something doubles every 10 minutes? Every 10 minutes. So for example, let's just say bacteria, right? Bacteria doubles every 10 minutes. So since it doubles, the rate would have to be 2, but H in this case would be 10 because it takes 10 minutes for it to double, right? So that's basically what H is. And finally, let's do one last example, which is, let's do this. So if something grows by 3% per quarter, So if it grows by 3%, so clearly R has to be 1 plus 0.03, which is equal to 1.03. And since it's per quarter, so in other words, quarter of a year, so it depends on, like, I guess how you define your time. But if we define our time in terms of a year, then H would be 1/4, right? If we defined our time in months, then H would be 3 months, right? Because a quarter is 3 months of the year. Okay, so based on this, let's just do a couple of problems and see how we can get the solution. Say for example we have, so here's number one, a city, right, has an initial population of, say, 1,000 people. 1,000 people. And it grows by 2.4% per year. So what's the population? What is the population after 3 years? Okay, so let's basically look at all the variables, right? So do we have A initial? A initial is, yes, we have A initial, which they said was 1,000. So we have 1,000 people. Now, let's look at R. What is R? R, they said it's growing by 2.4% per year. So R would be 1 plus 0.024, because that's 2.4% as a decimal is 0.024. So in other words, it's 1.024. Okay. H, since they've already said it's per year, so H in this case would have to be 1, right? And all we have to do is find the population after, so we need to know what A final is. So according to our equation, A final is just equal to A initial. I'm just going to write I for initial, times R to the power of T over H. So A initial is 1,000, R is 1.024, right? T is 3 years, this is the amount of time, so T is 3, and H is 1, so we just have to plug that in, and actually I haven't even plugged that in myself, so let me just do it as I'm doing it here. So it's 1.024, I'm just doing this on my Mac right here, to the power of 3, so what I'm getting is 1.024 to the power of 3, so what I'm getting is 1,074. So roughly speaking, it'd be 1,074 people after 3 years. So that was the first question. Let's do another question. So in this case, say for example we have 3,000 bacteria. Okay, 3,000 bacteria. I'm not going to write the question because I feel it just takes too long. And it doubles at a rate of every 15 minutes. Okay, so the question is, how much bacteria do we have? So bacteria after 1 hour, right? So how much bacteria do we have after 1 hour? So again, I'm just going to go right into the equation because we have to find A final, so that's AF. And it's equal to A initial, which is AI, R to the power of T over H. So one important subtlety is that the T and the H have to be the same unit. So just keep that in mind as we're doing this question. So initially we have 3,000 bacteria, okay? R is doubling, so therefore R has to be 2, okay? The question is how much bacteria after 1 hour. So typically we would think that, oh, okay, well, if it's 1 hour, we might put 1 over here, and H, they said every 15 minutes, so this would be 15. But however, keep in mind that this is in hours and this is in minutes, and that's not good. It's inconsistent. Both of these have to be the same units. So if we do that, right, if we want to keep everything in the same units, 1 hour is basically 60 minutes. So we have to deal with it this way. So if we plug this in, it's really just 3,000 times 2 to the power of 4. 60 divided by 15 is 4. And let's just do that here. So 3,000 times 2 to the power of 4. And that's 48,000. So the answer in this case is 48,000. Okay, so I hope that helped. In the next video, I'm going to talk about compound interest. So I'll see you in the next video.